Hello everyone, thanks for having me here. I'm Ji Yan, and on behalf of my co-authors Lee Sun, Tomas Krajnik, Tom Duckett, Nicola Bellato, I'm glad to share with you some of our research experience in long-term robot autonomy, especially from the perspective of robot learning. As a service robot, one of the expected capabilities is to run for a long time without human intervention. This long time may not refer to hours or days, but weeks, months, or even years. Long-term robot autonomy comes with many challenges, such as endurance, which also happens to be expressed in the word autonomy. Our research has been focusing on how the robot responds to changes in the environment and when it needs to travel between different environments. An example that already exists in our lives is the robotic vacuum cleaner. Except that it needs to manually replace some cleaning parts from time to time, it can already be called long-term autonomy in its work somehow. However, this long-term autonomy is related to the complexity of the service provided and what kind of devices the robot relies on to implement the service. In fact, more complex tasks and more intelligent implementations will pose more serious challenges to long-term autonomy. One of the enabling methods for long-term autonomy is robot learning, which is the intersection of robotics and machine learning. We believe that robots with autonomous learning capabilities are very much in line with people's imagination of future robots. Specifically, as a learning individual, a robot should show some initiative in learning knowledge as well as applying the results of learning. In our research, we put forward several more explicit requirements for robot learning, namely learning should take place in situ, on the fly, spontaneously and automatically, academically called robot online learning. Around this learning paradigm, two other related issues, corresponding to the input and output of learning, have naturally become our concern. One is, how to obtain useful and sufficient learning data through robot perception. And another is, how to ensure the real-time performance of the integrated system under the limited onboard computing resources of the robot. Here are some well-known things, but please let me still repeat them to make the whole story more coherent. So the perception of robots is typically divided into proprioception like by-wheel encoder, IMU, thermometer, etc., and exteroception such as through LiDAR, camera, sonar, etc. From a long-term autonomy perspective, proprioceptive data are relatively easy to interpret and model as the objects the sensors measure are essentially invariant. For example, the health monitoring of the battery of the robot. While the exteroceptive data are more complex and unpredictable, for example, you may know that a particular corridor will be crowded at a certain time, but it is somehow hard to predict the exact trajectories of people going through it. Clearly, exteroceptive data have a greater impact on long-term robot autonomy because they actually close the feedback loop between the robot and the world. So the next question might be, which sensors are suitable for long-term autonomy? This may not be easy to answer in one sentence, because sensors with different modalities typically have their own advantages and disadvantages. For example, cameras can provide color and texture information to help capture rich environmental semantics, but are unfortunately affected by lighting conditions. LiDARs can usually cope with the latter, but the data generated is just a set of coordinate points in 3D space, whose sparsity increases with the measurement distance, which is difficult to interpret. In addition, if considering indoor extreme conditions such as fire, or various outdoor weather conditions such as rain, fog and snow, the aforementioned two types of sensors may fail. At this time, adding another modal sensor such as a millimeter wave radar may be a needs. Here are a few images showing some of our previous work with mmWave radar. The figure on the left shows a simple experimental setup we made including a 2D LiDAR, a mmWave radar, a handheld smoke generator, and an RGBD camera just for recording the ground truth. The top right GIF shows that under normal conditions, that is, in the absence of smoke, both LiDAR-based detection and mmWave-based detection work well. Instead, the GIF on the bottom right shows that LiDAR is greatly affected by smog, while mmWave radar is pretty robust. So our answer to the previous question would be to use a robot perception solution based on multimodal sensors. Here we have selected 3 different examples. The first one is a Toyota HSR robot, which is still in prototype development. In addition to having an RGBD camera and a 2D LiDAR, it also has a stereo camera and 2 fisheye cameras. The second is a Xiaomi sweeping robot that has been mass-produced commercially. It can be seen that it is equipped with a 2D LiDAR and an RGBD camera. The third is the Apollo self-driving car in the commercial testing phase, which is equipped with some 3D LiDARs, cameras, radars, and other sensors. An issue that accompanies the use of multimodal schemes is that of data and information fusion. So here are just 2 common examples: low-level data fusion such as pixel-to-point matching of images and point clouds, and high-level information fusion such as fusion of detection results of different object detectors, for example for multi-target tracking. And usually, high-level information fusion comes with a higher demand for AI. For example, what if there are different interpretations of the same target based on the same or different data? So one of our proposals is to use odds, since it was proven many years ago that it can account for implicit interactions between different sensors. Of course, we have a prerequisite here for using it, that is, the information given should contain a certain degree of confidence. To end our topic on data, let's remind ourselves that service robots are often mobile. Thus, in some cases the robot may want to actively explore some information rather than just passively wait. One of our work in this area involves spatiotemporal modeling of the place where the robot works for a long time to understand the changing laws of the dynamic environment, so that the robot can intelligently plan its tasks, such as updating the environment map when there are no people. So we've mentioned before that one of the challenges of long-term autonomy is changes in the environment, and some of which are fast like pedestrians, some are slow like layouts, some are regular like seasons, some are random like human clothing. In theory, it is difficult for static models to adapt to such changes. Therefore, the model should be updated in time. In order to better explain our research positioning, that is, online learning, we use offline learning and incremental learning as references. So as shown on the right, offline learning is similar to offline programming common in industrial robotic arms, meaning that the model is fully trained before being deployed to the robot and remains unchanged during the robot's operation. To this end, data is pre-collected and often annotated to guarantee the final obtained model performance. Incremental learning can be online or offline. It can handle continuous data without imposing timeliness. It also allows for human intervention when necessary to ensure the iterative learning performance of the model. This learning style puts more emphasis on the preservation of knowledge and the avoidance of catastrophic forgetting. Instead, online learning means that the robot learns autonomously during operation without human intervention. Timeliness is another important feature of this learning method, that is, to learn quickly and apply the learned model immediately. This is a general formalization of online learning. Suppose that the total number of data we can finally get is d, but at a certain time t we can only get data from 1 to t-1. Online learning is designed to predict the corresponding output y for the input x at the current moment based on the data that has been observed, that is dt-1. So since we don't have access to all the data at time t, we want to make a decision each time that is close to the decision we made when we finally got all the data. Therefore, the optimization goal of online learning can be defined as regret, where W* refers to the model parameters obtained after getting all the data, and L is a loss function. Obviously, getting all the data is unlikely to happen for long-term robot autonomy. Additionally, a unique challenge that robots face is that the incoming data is often not annotated. For the first problem, it's a bit of a mathematical infinity, so we conduct a stability analysis of online learning by adopting a limit. A simple practice regarding this formalization is to set corresponding performance expectations based on some established metrics, such as those determined by offline-trained baseline methods, and then use these expectations to guide online learning iterations. The figure on the right gives an intuitive illustration. Once the model performance of online learning falls within the tolerance range of the expected value for a period of time, we consider that the model performance has stabilized. At the end of this talk, I would like to mention some elements about deploying, including but not limited to learning systems on robots. As we all know, robots may have more obvious requirements for the real-time performance of the system than other fields. The current robot presents a relatively complex form both in terms of hardware and software architecture. Therefore, reasonable allocation or say occupancy of computing resources needs to be considered, especially when we want to deploy the system to the edge. This involves the integration of software and hardware. For example, you might want to deploy system security and control-related modules to the CPU side, while deploying heavy visual computing or deep learning stuff to the GPU side. In addition, although the computing power of hardware is getting stronger and stronger, we still believe that the complexity of the algorithm should be considered, from design to implementation. Finally, the implementation of the code sometimes brings us some performance surprises. Here are some QR codes pointing to some of our practices, for community reference. I hope you enjoyed this talk. For more information, please check out our paper. Thanks for listening.